is first set of notes 1.1.1. It's about levers, wheel and axles, and pulleys, and they're all kind of the same family of simple machine. So simple machines, mechanisms that change the force or the distance the force is applied through. And usually what you're going to be doing is you're going to be increasing the distances a force is applied through to increase the output force. And the types we'll talk about today: lever, wheel and axle, and a pulley. Other kinds of simple machines we'll talk about at some later day are inclined plane, wedge, and screw. And again, those are kind of all in the same family of simple machines. Right, we're going to spend most of the time when we do simple machine stuff actually calculating things like mechanical advantage and stuff like that. Now, you've probably did simple machines before. We're going to do them a little more difficult here, like big, large compound machines, but we'll do those. Look at those later on. All right, so mechanical advantage is the ratio of the magnitude of the resistance and effort forces. Also, the ratio of the distance traveled by the effort force and distance traveled by the resistance force. So those are two ways to calculate it. You calculate it to figure out like what your machine's going to do. You're missing out because normally this is like an animation on the PowerPoint. If we have time at the end, I can show you. It's really kind of like janky animations, but you'd appreciate it. All right. So mechanical advantage of 4-to-1 tells us that the effort force is 4 times less than the resistance force. So you can, with a mechanical advantage of 4-to-1, you can push something 4 times heavier than the force you apply. Does that kind of make sense to everybody? And but the distance traveled is going to be 4 times greater. So with this wedge here, you'd push it up the ramp, and you'd have to use less force than just lifting it straight up, but you'd push it 4 times farther. So for all our simple machine stuff, we're going to be sacrificing distance. So we're going to increase the distance, but it results in an increase in force for us. All right, work is the force applied by an object times the distance traveled, and that distance has to be parallel to the force for it to count. That kind of makes sense. So work is just force times distance, but the distance has to be in the same direction as the force being applied. And we'll talk more about that kind of later in the. All right, and no matter how we use a simple machine, the work remains the same. So it takes the same amount of total, and work is kind of a measure of energy. It takes the same amount of total energy whether you use a simple machine or not. And usually, like for this ramp example, it would actually take a little more energy because you're going to have more friction going up the ramp than you would lifting it. And mechanical advantages are all kind of compared to 1. So if mechanical advantage is greater than 1, you're using less force but a greater distance. If it's less than 1, you're using a greater force and a smaller distance. Kind of make sense to everybody? And you can't be less than or equal to 0. So ideal mechanical advantage is a theory-based calculation, so it's going to have some impact on the real world, but it's not going to be perfect for the real world. So we're not taking friction into account in these, and that's usually going to be a pretty big loss for a lot of simple machines. So the ideal mechanical advantage is equal to the distance traveled by the effort force divided by the distance traveled by the resistance force. So like on the ramp, it would be, let me draw the ramp here. You draw the ramp. The distance of the effort force would be this side. The distance of the resistance force would be this side. Oops. So it'd be how high it went, because you're trying to lift it, would be the resistance distance, and the effort distance would be how far you actually pushed it. Does that kind of make sense to everybody? Mechanical advantage, that is where friction losses are taken into account, and that's going to be the magnitude of the resistance force divided by the magnitude of the effort force. So if you look, and for actual we'll talk about that later. Think of a machine that has a mechanical advantage of greater than 1. It's first period, I know, so it's going to be probably rough to get answers out of you guys, but like things like anything that has a larger turning thing than what's being turned. So like the knob on a faucet, like outside, that is a mechanical advantage greater than 1 because your distance is going to be greater because that circle is bigger that you're turning on the outside than the little axle you're turning on the inside. Does that kind of make sense? Anybody think of something that has a mechanical advantage of less than 1? So a lot of times when you have like gym machines, they're actually designed to have a mechanical advantage less than 1, so you have to apply a greater force than you would normally, so they don't have to put as much weight on there. And you can usually notice that. It's like, have you guys ever used a machine that like you do like a bench press on or something like that, instead of like actual weights, just like the machine? If you watch what happens when you push up, the actual weights you're lifting, they're usually like above your head or whatever, actually go up farther than you're pushing them. So you're increasing the force, and that increases the distance the other weights are going to move. So you have to apply a greater force, but the weights go a farther distance. Does that kind of make sense? So our first type of machine we'll talk about is a lever. And it's just a rigid bar that you're going to push down or lift up on one end, and the other end's going to go down or up, or it's just a bar with a pivot point at the end you lift up, and the resistance force you're trying to lift lifts up as well. This kind we'll talk about is a first class lever. The first class lever has the effort and resistance on opposite sides of the pivot point. And the mechanical advantage can be greater than or less than 1 depending on where that pivot point is. So if the longer side is the resistance side, the mechanical advantage is going to be less than 1. And if the longer side is the side of what you're trying to, the side you're applying the force to, then the mechanical advantage is going to be greater than 1. Right, second class lever. This time the fulcrum is located at the end, or the pivot point is located at the end. The force, what you're trying to lift, is in the middle, and the force you're applying is at the end. Can anybody think of an example of this type of lever, where you apply the force at the end? Tim? Wheelbarrow. So if you lift up at the end, what you're trying to lift is in the middle, and the pivot point would be the wheel. Does that kind of make sense to everybody? Third class lever. This time it's still located, the fulcrum or pivot point is still located at the end, but now the resistance you're applying is at the end, and the effort force you're applying is in the middle. Now, there's many third class levers in life. Can anybody think of an example of a third class lever? One of the most common ones is a golf club, actually. For a golf club, you're kind of the pivot point. The head of the golf club would be the resistance, and you apply the effort force between you as the pivot point and the head of the club, which is the resistance. Does that kind of make sense? A moment, so the turning effect of a force about a point is equal to the magnitude of the force times the force that's perpendicular to the distance from the pivot point. And that doesn't make a whole lot of sense, but so the moment's going to be this distance times that force. So you see it's there. You go find your force and go shortest straight line distance to the pivot point is going to be your distance. So it's that times the shortest straight line distance to the pivot point. We'll talk more about that later on when we get to civil engineering stuff. And a torque is a force that tends to produce rotation or torsion. Moment and torque are usually the same thing. Alright, so this is an example of a sample lever moment calculation. So in this case, our distance is going to be 5.5 inches, distance from there to there. Effort force is 15 pounds. So just multiply those two together, you get 82.5 pounds. Any questions about that one? Alright. So when the effort force and resistance moments are equal, lever it's in static equilibrium. If it's in static equilibrium, that means that it is not changing what it's doing. If it's at rest, it stays at rest, which is usually what we're going to be talking about with motion, because it's kind of a civil engineering thing and you don't want your bridges to be rotating generally. Or if it is rotating, it's rotating at constant velocity. More an example of the problem we'd be doing with this. So if this is in static equilibrium, we're going to figure out what that distance is if we know these two forces. So if it's in static equilibrium, the moments for both have to be equal. So we found this is 82.5 by multiplying 15 by 5. The other side, 36 2/3 pounds times whatever that distance is has to equal that. So divide both sides by 36 2/3, and this is something that drives me nuts about their PowerPoints. They start off with 2/3 there and then randomly change it to 36.66 there. They do that all the time. It should be 36.66 everywhere, but that's okay. So when you divide that out, you get 2.25 inches. And we're going to be doing more examples of practice problems like this later on. Lever ideal mechanical advantage. So our ideal mechanical advantage is the effort force, or the effort distance over the resistance distance. So our effort distance, if we had like a lever, and what class lever is this? First. So they're on opposite sides of the pivot point. So when you think about the distance the effort force would go to, if you kept pushing, it'd go around in a big circle like that, right? So our effort distance is going to be the circumference of that circle, and the circumference of the circle is 2 pi r. So it's going to be 2 pi times the length of that lever arm. And the same thing for the resistance, because if you push this down, the resistance is going to go around like that. And then it's going to be in a circle as well, so its distance would be the circumference of that circle. The nice thing when you do this is the 2 pi's cancel, so the ideal mechanical advantage just ends up being the arm length for the effort, so that length divided by the resistance length. It's going to make sense to everybody? Actual mechanical advantage, resistance force divided by effort force. So in this case, it's going to be our resistance force is what we're lifting, so that'd be 32 pounds. And our effort force is the force we use to lift it, so that'd be the effort force. Alright, so when we calculate that, we get the actual mechanical advantage is 2.2, so it's 2 to 1. The ideal mechanical advantage is going to be this distance divided by this distance, so that's going to be 2.44. So why is the ideal mechanical advantage larger than the actual mechanical advantage? What force? Alright, go ahead.
Because like one takes friction.
Yep. The actual mechanical advantage takes friction. So that should always be smaller than your ideal mechanical advantage. Every once in a while, if you get this to be bigger, something kind of went wrong, and my guess is at some point in this class you'll design a lever that something goes wrong, and I'll ask you to figure out why your ideal is great or is less than your actual, but we'll get to that later. Efficiency. So this is the ratio of actual mechanical advantage to ideal mechanical advantage times 100, so you get a percentage here. So for our last one, it would be 2 was our actual mechanical advantage divided by 2.44, so our efficiency was 82%, and no machine is ever going to be 100% efficient. And you lose almost all of your efficiency due to friction in machines. Wheel and axles. So you have a wheel. It's a lever that's fixed to a shaft. So a wheel and axle acts just like a lever. So you have your pivot point would be there. Your effort force is going to be turning the axle, so that would be like applied right there. I'm sorry, your resistance force would be where the force turning the axle right there, and your effort force is applied out here. Do you guys kind of see how that looks just like a lever? And what kind of lever is that? Second class. So this would be your effort force and your resistance force. Alright, so there are two different types. You can have a wheel driving an axle or an axle driving a wheel. What's an example of a wheel driving an axle? There's like 3 of them right there. Steering wheel in your car. So you have the wheel and the axle is here. What about a axle driving a wheel? Car. So the wheel on a car is an axle driving a wheel. So axle turns, and that axle then turns the wheel. That kind of makes sense? So wheel and axle, IMA, ideal mechanical advantage is effort distance over resistance distance. So we've got 6 inches for the axle radius and 20 inches for the weight radius of the wheel. So we want to find the circumference of both of them, so we can do pi d or 2 pi r. So I guess those are the diameter they gave us. Doesn't really matter. You can either do the diameter of the wheel or axle, or the radius of the wheel and axle. It's going to work out the same way, because the 2 pi or the pi's are going to cancel. So the if we do the axle driving the wheel, we're going to have a mechanical advantage of less than 1. So it's going to be, our effort distance is going to be the axle radius or diameter divided by the diameter of the wheel, and we'd get 0.3 in this example. And the IMA, if it's the wheel driving the axle, would be the opposite, so 20 divided by 6, so you get 3.33 as your ideal mechanical advantage. Alright, so actual mechanical advantage of this is going to be if we have 70 pounds of force being applied to turn it, and you end up with 200 pounds turning the axle. So if the wheels driving the axle, our resistance force is 200. And our effort force is 70 pounds. Divide those out, you get 2.86 for our actual mechanical advantage. And if we found out the efficiency, we'd take our actual mechanical advantage divided by the mechanical advantage we found before, and it'd be about 86%. It's still a lever. It consists of a wheel with a groove that you put a rope or cable over, and you can multiply or get mechanical advantage out of that as well. So, ideal mechanical advantage of a pulley. Ideal mechanical advantage of a pulley matters how many strings there are lifting whatever the weight is. So, if we look at this one, it has an ideal mechanical advantage of 1, because this is the only string or cable pulling up in it. This one over here is pulling down. Does that make sense to everybody? This one has a mechanical advantage of 2, because this one is applying an upward force and this one is applying an upward force. Does that make sense to everybody? So if you have a pulley shape like this, you can lift a 10-pound weight with a 5-pound force. This one, you have to use a 10-pound force to lift a 10-pound weight. Anybody have any questions over that? All right, and we'll talk a little bit more about that later on. So now we have pulleys in combination. So we're looking for how many ropes we have that are lifting the motorcycle here. So first off, the trickiest one is often this one. Does this one count? Is it applying an upward force? That one. Is that one going to count? Nope. So that one does not count. What about all these other ones? Do count. They're all going to end up applying an upward force to the motorcycle. So we've got our mechanical advantage would be 1, 2, 3, 4. So the ideal mechanical advantage of that pulley system is 4. Do you guys kind of understand how you can figure out the mechanical advantage of a pulley from that? You just got to count the ropes, and you don't count the ones that are pulling down. So if you're pulling down it doesn't count, but if you're pulling up on it, it does. Alright, so compound machines. These are going to be the hard problems we do later on, but so you can start seeing it. If you have two different simple machines, you just multiply the ideal mechanical advantages of both of them together. So for example, this one, we'd have the mechanical advantage of that pulley would be what? 2. And then we'd figure out the mechanical advantage of the lever here. And what type of lever is this going to end up being? Second class, because we have our effort's going to be right here, resistance is going to be right here, so on the same side of the fulcrum, and its effort is further away than the resistance, so it's second class. So we do our effort distance, which is 12 feet, divided by our resistance distance, which is 4 feet. Divide those, so that would be our ideal mechanical advantage of the lever. Pulley is 2, multiply those together, we get 6. Any questions on that one? Pulleys in combination. So this is a different kind of pulleys. Last time you saw how the pulleys look kind of like this. The pulley, 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 and they were kind of, this is going to be a bad drawing, but it was all like kind of wrapped around the same thing. That's a terrible pulley, but you get the general idea. You see how this one, they are more separate than they were in the previous one. So, and they're attached at different places. So every time the pulley is attached to a different ceiling, you have to consider a different, like you have a piece of the pulley attached to something, it's going to be something different. So what's the mechanical advantage of each of these pulleys? So if we just look at this pulley right here, what's the mechanical advantage of that one? 2. So you have 2 upward forces. What about this one? 2. And this one would be 2 as well. So so when you have the separate pulleys, you have to multiply each mechanical advantage of each pulley together. In this case, the mechanical advantage total would be 8. So you can't count the strings this time. So if you just counted the strings, it would be 1, 2, 3, 4, 5, 6. So because they're separate, you have to multiply the ideal mechanical advantages together of each individual one. Alright, so actual mechanical advantage of a pulley. The ideal mechanical advantage of this one we said is 4, because it's got 1, 2, 3, 4, and this last one doesn't count because it's pulling down. So if it's using 230 pounds of effort force to lift 800 pounds of resistance force, actual mechanical advantage is going to be resistance force divided by effort force, so 800 divided by 230 gives us 3.84. Then we calculate our efficiency is 3.48, not 3.84. 3.48 divided by 4 is 87%. A common misconception about pulleys is that angles don't matter. Angles do matter. So if the pulley is not if the strings of the pulley are not parallel to the force you're lifting, it's going to change. We aren't going to have to do this in class, but if you do have things that, like the rope's at an angle, the force you have to apply is greater. So the best situation you can be in is if everything is parallel. So remember I said if it pulls up, you count it. It's not always absolutely forever true. If you're pulling something down, so let's say you're pulling like a spring on the ceiling down, this one then counts even though it's pulling down. So if it's pulling the opposite direction of what you're trying to pull, you count it. Usually that's going to be anything pulling up, you count. But if you're trying to pull something down, a rope you pull down counts as well. Does that make sense? All right.